Hi, everyone. Our next speaker is Harrison Grodin, and he will give a talk on symbolic manipulation in Julia. Let's welcome.
Hi, everyone. So today, I'm going to run through how we can do symbolic algebra in Julia. I guess without further ado, let's get started. Okay, so say you happen to be in the Julia community, 50-50 chance you want to do pharmacometric modeling. So what are you going to do? You probably want to come up with something like this, this PKPD model. This is from Pumas.jl, a project I'm on the team for. You can do this already with differential equations, but you'd really like to represent this in a more elegant form that we can do some transformations on. So, how can we do this? The answer is pretty straightforward. You might have guessed from the talk name. We can start representing it symbolically. So you might want a piece of software that looks something like this, right? You'd specify your parameters of the system as t, sigma, rho, beta. You'd make your variables x, y, z, all functions of t, and you make your derivative with respect to t. And then you continue to set up your equations, right? You say that the derivative of x is equal to, defined as equal to sigma times quantity y minus x, and so on, and you build your ODE system. Well, in case you were hoping this kind of system exists, then, there you go. It's called ModelingToolkit. So this is not going to be the primary focus of this talk today, though, because I want to talk about a specific issue that we have in ModelingToolkit. So take a look at the top. Often whenever you take a symbolic derivative, you'll end up with things like this, right? It's sigma times 0 plus 1 times y. And in your head, you're looking at me and saying, it's just y. Why do you want to represent it like that? And I agree. There's no reason that we need to have this extra build-up as far as the term goes. And similarly, you just want to do symbolic differentiation in the first place. We'd like to be able to have that bottom thing work. We want to be able to differentiate sine 2x and get 2 cos 2x. But there's a bit of machinery that we have to build up. So we're going to take some advice from Thoreau and simplify. Sound good so far? So here's the kind of intuition behind what you want to do with symbolic algebra. You're going to specify a bunch of transformations you want to do, starting with some form that you don't like that much and turning it into a better form. So you'll say, if you ever see an x plus 0, turn it into an x. If you ever see an x times 0, turn it into a 0, etc. So the kind of colloquial explanation would be find the bad things and replace them with better things, right? Pretty straightforward. So I have a few more interesting examples. So suppose you take a look at sine of negative theta. What you want to turn that into is negative sine of theta. At the bottom, I kind of included this implicit universal quantification. You want for all theta that this is true. And sometimes you want a bit of a qualifier as well. So for example, if we run through, you might want to say that the inverse of x rewrites to x, given that x is not equal to 0, for all x, though. So this given is probably something that we want to include. We want a condition because often you want to specify something that only applies in some cases. So congratulations. If you were thinking all of this, you've just invented term rewriting. This is a field of logic and mathematics which deals with these kinds of transition systems. So to quote Bruno Buchberger, the guy who's responsible for Grosvenor bases, the kernel of the mathematical language is a higher order conditional rewrite language, emphasis on rewrite language, with sequence variables. So there's a lot of qualification going around there, but generally speaking, the important part is rewrite language. We want to build a rewrite language in order to do this effective symbolic manipulation. So let's take a crack at it. So again, with these kinds of rules, you may have noticed a caveat. Often we have these kind of redundant rules in our head where you want to say x plus 0 rewrites to x, but also, come on, 0 plus x also rewrites to x. I really don't want to have to specify that because just looking at the term, it feels true, right? And you'd end up with all these annoying overlaps that you'd have to deal with in the case that this wasn't implicitly true. So we want to build some kind of machinery in for that as well. How do we do it? Well, we'll just allow people to specify that you want to have these certain axioms. The two important ones are associativity and commutativity. The idea is that sometimes you want to just tell the system, oh, you can reparenthesize however you want. That's associativity on the top. And sometimes you want to be able to commute. You want to be able to rearrange the sub-expressions in any way you want. And these let your rewriter have a bit more information that can be efficient, as we'll soon see. So if you were thinking all of this, congratulations, you've invented term rewriting modulo equational theories. So again, there's a bit more to this than regular old term rewriting, but it seems worthwhile, right? It'll let our users have a bit of an easier time. So the goal that we want is a canonical form, right? You're going to feed in some symbolic expression, and you want the unique, simplest form. And I put it in green because it's what we want, just so we can keep track of it. So let's see. As far as the mathematics goes, in order to have a canonical rewrite system, it has to be both terminating and confluent. So give me 1 second. I'm going to drink some water, and then we'll write a system that has these properties. We'll write a system that checks if any rewrite system has these properties. No, we won't. We really won't. I was hoping to get some, confused glances there. We are not doing this because it's mathematically impossible. These two properties are undecidable about any rewrite system, unfortunately enough. So even though I really wish that I could write a program that would guarantee you your rewrite system terminates, it is not possible. So what can we do instead? Well, first, let's just note that the reason for this, one of the ways that you could derive this is true, is that a term rewriting is actually Turing complete, which means it has the computational power of any old programming language, right? So since it's Turing complete, if you had this termination property, it is guaranteed to be undecidable. You can't do this in Julia either. You can't tell me if a program's going to terminate. Well, what do we do about this? I propose an ingenious transformation of the previous slide where we make that green. So the idea is, rather than taking Turing completeness as the bane of our existence and fighting this losing battle, we're going to take advantage of it, and we're going to treat term rewriting like the programming language it is. So the idea is kind of as follows. We're going to take a rule like the thing on the left, which is easy to parse and easy to understand, just telling you that you get rid of these zeros, and turn it into an efficient piece of Julia code, like the thing on the right, where you check that the root is plus, and you check that if the first argument is 0, then return the second, etc. Cool. So applying these rules is actually pretty easy. Once you know what the variables are, building up the term on the right-hand side is straightforward. There's pretty much an obvious way to do it. If I gave you x and I said build the term x in rewriting x plus 0 to x, yeah, no problem. The issue comes in whenever you want to find where to apply these rules, right? It's pretty tough to look at all these axioms and look at this massive term and say, yeah, by the way, there's the simplification you were looking for. So assuming that the first part is easy, we're going to just take a crack at the second part. We're going to see how we can efficiently match. So we're going to think of this kind of like a compiler. So the idea is we can do a lot of transformation and derive a lot of information before we've seen a single concrete term. Once you've told me the patterns that you're considering, we can do a lot of thinking in advance to figure out how to efficiently deal with things. So suppose you wanted to make a free term, a term under no axioms, then it's pretty easy. You just make that term. You get the root, you get the arguments, and you just build that term object. Ooh, that looks weird. Suppose you wanted a commutative term. Well, you want a normal form, right? You want a unique form under commutativity. That's pretty easy. You have this greater than sub t, even though the sub t is rendering strangely. And you check if s is greater than t in your total ordering over terms. If it is, you flip the order, otherwise you keep it. So this is cool because if I have any two commutative terms, I can tell you for free if they're equal. Here's a quick aside about AC terms. You can actually get a lot of efficiency out of these representations. So you might consider a term like, A times C times C times A times C times B times D, and this is going to take up a lot of space, and it's going to be annoying to match against. You can just turn it into something like this dictionary for this efficient representation, right, where you map the term to its multiplicity. Cool. Let's now think about how we're going to make this matter efficient. So suppose that you had a free function symbol f and a commutative function symbol g. How many ways are there to match this term? Like 4, right? Both commutes. So you could do yz, xy, both of those terms in that order. You could try yz and then yx, etc. But we can be more clever, right? Because we know that for free, we can match x immediately because it's under a free term. So then, looking at the third term, we can match x, and therefore, by process of elimination, we know what y is. And therefore, by process of elimination in the middle, we know what z is. So it turns out this is actually a fixed term, right? You know exactly what the match should be for free once you match it. There are no permutations to check. So we'll try to be efficient here. Let's see. So as far as the matcher goes, we want to build a matcher from this term. So this is kind of pseudocode based on the actual code that we have. But the idea is, given a term and a set of variables you already know about, you want to build the matchers for the subterms. So first thing, we'll keep track of the symbols and the variables and the alien subterms, the terms that are not free. So down here, we'll build the context, we'll look through the tree, and keep track of all the symbols and variables and aliens. And then here, we'll find the best permutations to match the aliens in. In that previous slide, we wanted to do the second one, then the first. So we'll do that computation here. It might be kind of expensive, but who cares? It's compile time. Something actually pretty neat is we can deal with compiler optimization. So suppose you had an AC term. Unfortunately, matching under associativity and commutativity is NP-complete. That's not the best. It takes a long time to match. It could be exponential. However, most patterns that you're going to encounter are in this nice form where it's just a variable and then a bunch of constants you want to throw away. Like x plus 0. You can just delete the 0 and put everything else on x. No solver required. So we can do this kind of neat setup where we say, OK, if you're in a nice form, then we'll just create the fast matcher, and we can compile more specially. And otherwise, we'll do the full slow matcher as this backstop. So in phase 1, we just have a pattern, and we want to compile it. We first create these classes of patterns as humans that we want to match efficiently. And then we can build the matchers themselves. So let's see. Phase 2a, we get a subject. I'm going to kind of run quickly because I want to be able to show a demo of this. So you get this subject, and now you want to match it. So fair enough. You want to match with certainty as much as you possibly can immediately, and fail early if you can tell that it's not going to work out in the end. So this is a lot of code. Don't worry too much about it. The idea is it has 3 sections. Excuse me. So we start off by matching all those aliens in the right. Oh, sorry. We start off by matching the correct, by matching the free term, assuming this is a free matcher. And then we match the aliens in the right order. That's this middle for loop. And finally, we return this subproblem. And what is the subproblem? Well, this kind of encodes the uncertainty, the permutations. Because in reality, we only care about one match for the most part, right? We just want to rewrite once. We don't care about all the matches. So sometimes we'll have to iterate twice if the first match doesn't meet the condition that we gave it. But generally speaking, the first is good enough. So we want to encode that computation lazily. So finally, you want to compute this result. It's just a simple iterator. There's an iterator called matches that we have. You feed it a subproblem and the partial substitution that you built, and you iterate through it. That's the API. Often, we're actually experiencing low test coverage on the second method, just because you so rarely need to iterate through more than one time that why are you going to match the second one? This is called Rewrite.jl. So that was a lot of explanation, but the idea is that's kind of the fundamentals of how we're going to do symbolic algebra. It's all in Rewrite.jl, which is this efficient term rewriting engine in the Julia language. And this is available to use. So I'm going to give a quick demo of that. Let's see. Can everyone see this OK? So we'll load up Rewrite, and we'll load up benchmark tools. And we'll just do some simple addition on natural numbers. This is not the most efficient, but I figured it would be worth showing. It's a pretty simple demo. So we'll say z and s are both from the free theory. Z is going to represent the 0, and s of n is going to represent the successor of n, one more than n. And we'll define addition recursively. So we'll set that up in the theory. We'll say the rules for addition, given variables x, y, are x plus z should just rewrite to x, and x plus the successor of y should rewrite to the successor of x plus y. And it builds us this nice little function, add. So if we take a look at what this is actually doing under the hood, using the pipe operator, mind you, it'll generate this Julia code, which is actually doing the matching. So you'll see, for example, up here, it checks that it's a free term, and it checks that the top is plus, and there are 2 arguments, etc. So we can do it. We can rewrite things. Check it out. 2 plus 2 is, in fact, equal to 4. Yeah. OK, wait, but there's a caveat. So 0 plus the successor of a, given some arbitrary a, isn't as good. It gets us, 0, the successor of 0 plus a, because we didn't tell it about associativity and commutativity. So let's do that. We'll update our theory right here. We'll say, by the way, plus is an associative commutative symbol, and we'll set up our new rules as the same kind of way, but it'll create a better matcher. And now, not only is 2 plus 2 equal 4, but here we have 0 plus quantity a plus 2 is 2 plus a, and down here even we can say that's 4 plus a plus b. Kind of cool. So this is actually a normal form. This is what we wanted. And I have a quick demo, which I'll kind of speed through just because we're low on time. But we can set up some differentiation rules, too. This is really useful whenever you're doing those differential equations we started off with. So for example, down here, the differentiation x with respect to x is 1, and x plus 1 is also 1, and 3x plus 1 is 3, and whatever. Again, not an efficient representation. We're working on that, but for now it's a demo. So yeah, let me kind of wrap up. First of all, we're nowhere near done. There's so much more that we can do. First of all, more theories. It would be great to support associativity without the commutativity. We should be able to match with respect to the identity. There are lots more features we can add, like those conditions we showed earlier, and higher order rewriting, like sums and integrals. We want to have a bunch of good default rule sets for doing algebra. We want these large-scale optimizations like common sub-expression elimination. This lets us not redo computation on subterms. We want discrimination trees which overlap rules so that you don't have to do as much repeated matching. There are micro-optimizations like getting those last few nanoseconds and microseconds out of the system. We want to integrate better with other packages like ModelingToolkit. That's something that's going to be happening in the near future. It would be cool to have these heuristic checkers for the undecidable properties. So if you could feed in the set of rules and have it tell you that it's undecidable, or that it's that it's terminating even though that's an undecidable property, that would be kind of cool. And also, we'd love to extend this to solvers. So there's so much more work to do. The three packages I'm talking about today are Rewrite, which is the rewriting engine, Simplify, which is the algebraic simplification setup based on Rewrite, and ModelingToolkit, which is kind of at the top level for doing differential equation operations. So rewriting is just doing operations on trees, not this kind, but you know what I mean. So generally speaking, there's lots of stuff that people in the community can contribute to. I'm only one person, and getting all these features and more will take a lot of effort. So if you're interested in these micro-level optimizations, if you're interested in general algorithms, if you're interested in anything of the sort, feel free to come talk to us. We have Symbolic Manipulation in the main Julia Slack. Come chat if you're interested in contributing or even using our software. I have so many acknowledgments that they don't even fit on one slide. I'd like to thank my advisor, Jeremy Avigad. I'd like to thank Chris Rakakis. I'd like to thank the University of Maryland Center for Translational Medicine team and the PUMAS team. I would like to thank Stephen Eaker, who worked on a lot of the research that I was presenting here and was kind enough to communicate with me via email. Mason Protter, who was extremely helpful online in the Julia community. If you see him, say hi. He's awesome. And so many more people. Here's a ton of references, lots of books and papers and stuff, which are very much worthwhile if you're interested in this kind of thing. And yeah, with that, can I take any questions?
How does it deal with conflicting rules?
Oh, good question. So implicitly, we're kind of assuming that you provide a terminating and confluent rule system, which means that in the case that there's a conflict, it can pick either one, and it's guaranteed to converge back in. So we kind of just assume that the user provided us with a logical set of rules. It's a good question. Any other questions? Yeah.
I don't think I can get to a mic.
Yeah, it's okay.
What is the end user application you see benefiting from this first?
Yeah, so the question is, what's the end user application that we see being the benefit of this? So there are lots. In the same way that we do numerics all over the Julia community, we should be able to do symbolics as well. There are some really basic applications and things like simplification. But extending this, we can do lots of complex operations on systems of differential equations and everything. Should be pretty widespread. Any other questions? Yeah.
Have you done any like benchmark comparisons to things like SymPy or Mathematica?
Yeah, we've done a few benchmarks. I actually have that in here if we want. So if I just threw on, let's do our 2 + 2 = 4. So if we run this quickly on a benchmark, it should be pretty fast. It's running a bunch of them, but there we go, down in the REPL. So that's on the order of microseconds. It's not great for checking that 2 + 2 = 4, notably, but we're working on it. Generally, our matching is pretty fast, order of nanoseconds or a microsecond. So we're trying to make this fast. As that quote from Buchberger said, generally, Mathematica is a highly performant version of this. So if you're interested in optimizing Julia code, getting these few last microseconds out, that would be fantastic. Cool. Any other questions? guess that's it. Thanks so much.
Thanks, Mary.